really help us. And also remember that you can ask questions during live events, also from our main webpage. So without further ado, it's my pleasure to introduce our next presenter, Dr. Brian Klimowski. Brian is the meteorologist in charge at the National Weather Service office here in Belmont, Arizona, and he has served in this position for over 17 years. He went to graduate school at the University of Wyoming, and where he was involved with several weather modification research projects in North Dakota and in Northern Arizona. Brian is also a longtime friend and public presenter for the Flagstaff Festival of Science, and he's served on our board of directors for 10 years, and he's one of our past board presidents. Brian currently lives in Flagstaff, and he does not plan on retiring anytime soon, he says, which is great news for the festival as well as for our greater community. So Brian, take it away.
All right, thank you very much, Greg. And thank you all for being with us this evening for the Flagstaff Festival of Science and joining me on this talk. I really appreciate it. We're gonna have a good time. So what I'm going to talk about today is weather modification. We're going to talk about, can we control the weather? It's a fascinating topic that I'm personally very excited about. Like Greg said, I've spent some time with my graduate education studying and being involved with weather modification projects, which have been a lot of fun up in North Dakota, then as a postdoc in Northern Arizona. One housekeeping item. If any of you out there would like to just send a quick note through the Ask a Question box on the website, just so I can understand and see who's here today, I would love to hear from you. I would love to see who is behind this webcam that I see on my desk. That'd be great. So if you could just take a moment and do that, that'd be great. And we'll go ahead and get started. So, water is the most critical element of the world. I mean, really, water is so essential to life. It's a part of all of our lives. We see it in some form or another every day. And you can imagine a world that if we had control of this resource, this amazingly valuable resource, that we really would have incredible power. Imagine, if you will, if we could take a rainstorm and make the rain fall over any of our crops when we wanted it and where we wanted it. Imagine if we could, let's say, steer a hurricane away from the coast. Imagine if we could ensure that there weren't any more droughts. Imagine if we could make thunderstorms so they'd never be severe, but always beneficial. Or that we could make sure that a tornado never happened. Now, of course, controlling the weather to this magnitude isn't really something we can do. But what we can do, and what you're going to hear about today, is we can influence parts of the weather. We can influence parts of the physics that we see to benefit us in certain ways. It's really exciting. There's breaking research going on very recently. Actually, I'm going to share with you some of the most important weather modification research, which is breaking right now. It's actually going to be in an article which is yet to be published, but I just found out about it today. And it impacts the weather modification community as we speak. So let's go ahead and get started. Weather modification, and it can be broken down into two basic areas, and that is inadvertent weather modification and planned weather modification. The inadvertent weather modification is that which is done through unintended consequences of our human activities and just our presence. An example of this could be, let's say, in large cities that spring up, we have the urban heat island effect, where it's a lot warmer within the city due to the concrete and the asphalt that kind of soaks in the daylight heat and then re-radiates it at night. Or the impacts of aerosols is also one of the inadvertent weather modifications. Could be smoke, could be dust, which can influence cloud formation as well. The increase in carbon dioxide and the climate change, which is occurring as a part of that, it's also one of these inadvertent weather modifications. But that's not what I'm going to be talking about today. What I'm going to be talking about is planned weather modification. And that is efforts to intentionally manage or intentionally change some part of the weather for our benefit. It could be bringing more rain or snow to an area. It could be suppressing large hail so it doesn't damage crops. It could be dispersing fog at an airport. Now on my list here, I have a couple of other things like hurricane modification and lightning suppression. We'll talk a little bit about that today, but there really isn't much we can do about those yet. We'll get to that a little bit later. So there are weather modification projects going on all over the world at this time. Cloud seeding, for instance, is being done by many countries right now. There's a robust program in China where they're doing cloud seeding over very large of the Tibetan plateau, perhaps almost as large as the state of Alaska. They're trying to influence and bring more rain and snow to that area. And of course, during the Beijing Olympics, they were trying to prevent rain from falling over some of the venues, all through cloud seeding. Currently, 15 states across the Western United States also have active cloud seeding programs. We have hail suppression going on actively in several different countries up north in Alberta, in Canada, Argentina, Russia, Europe, and North Dakota, active hail suppression programs through cloud seeding. I mentioned North Dakota for one reason, and that's because I'm particularly passionate about that project there. Back in 1989, I was a part of what's called the North Dakota Thunderstorm Project, where we're investigating the conditions that caused hail to form. We flew through some amazing storms. I'll be talking about that in a little bit, but a lot going on in North Dakota. Fog mitigation is also common. Runways and airlines can be impacted by fog frequently, and we found actually some solutions to that problem. And like I said earlier, research in weather modification is progressing fast. There, with the more powerful computers we have, with instrumentation, which is cutting edge, we're finding out things and seeing aspects of the clouds that we never have before. It's a very exciting time to be in weather modification and to be studying the science and the physics of clouds. Now, where did all of this get started? Where did weather modification begin, and like when were the first projects? Really in the late 1800s, this started. There were European countries and communities that were impacted by hail, and they were looking for ways that they might be able to mitigate that. And the drought in the United States at that time also brought about some, can I say, quite innovative people to address that problem. But first, let's talk about Albert Steiger. Albert Steiger was a distinguished Austrian winemaker that saw his crops ruined one year through a severe hailstorm. And as he was looking at his failed crops, he was just kind of wondering what could be done to perhaps manage this. And he thought about the process of hail formation and how it starts from very small particles, or at least what the understanding of the science was, growing very large in these big thunderstorms and crashing to the ground. And he invented a unique device that he placed out in his vineyards. He tried it one summer. All of his neighbors were aware of what was going on. And all that summer, he had no hail fall on his vineyards. Was it a success? I don't know, but certainly he told all of his neighbors what was going on, and he tried it another year. Year two, he had no hail fall on his vineyards, and actually some of his neighbors put out his device as well. We're starting to have some success here. So 2 years without hail had people very excited in that area, many using his invention. And by 1900, this was about 2 years, only 2 years later, over 10,000 of his inventions were in northern Italy alone, and many others across Europe. You might say it went viral, okay? It went viral back in 1900. Well, this promoted the first hail suppression conference in 1899 in Italy, where 60 different instruments were on hand and discussed. And the conferences were held then every year for a number of years, highlighting new technologies in hail suppression. It looked like they were onto something. Now, what was this device he invented? What was this device that they were using? It was the hail cannon, indeed. And here's a picture, or an image from the Third International Congress on Hail Shooting. Hail shooting, they called it that time in 1901. These were huge megaphone-like contraptions, which took an explosion at the small end and then magnified it through this huge tube aimed at a storm that might be impacting their area soon. So what was the idea behind this at the time? The idea was that the sonic waves, or the sonic boom that would occur, these were loud explosions like TNT, or the loudest gunshot you could imagine going off, focused at the clouds. So the thought was that this would actually break up the smaller hailstones before they had a chance to get big. Or perhaps even if they were larger hailstones, it might break them up before they fall and cause damage. It was an exciting time. These were springing up all over, and you can almost imagine what it sounded like when you were in a vineyard or nearby and a storm was starting to approach. You would just hear these booms going on, boom, boom. It would often happen like at every 3 to 5, every 10 seconds. They would try to have one of these sonic booms go off, sending out this powerful energy, as they said, into the air. Well, it kind of looks like the science caught up to them after a couple years. And by 1902, there was great uncertainty into the hail cannon effectiveness. So what they did was they put together an experiment with 200 cannons and experimented them for 2 years. Well, unfortunately, hail fell. The experiment and the technology was declared a failure. And what's really amazing is how fast word got around, because these were effectively not used anymore. After over 10,000 were in use one year, it only took a couple years and they were gone after that. Well, Albert was an inventive sort, and he, kind of extended his scientific theory to thinking, well, if this sonic boom could break up hail, and maybe it doesn't in this case, maybe it could shake rain out of the clouds at times when you needed more rain to fall. So he tried that again and kind of called them vortex guns at this point, rain-making guns, and tried them as well. This picture you see on the image is a picture of one of these guns, which was actually being tested in Queensland, Australia, where they were having a drought at that time. And they hired Albert and some other folks to bring out a number of guns and test them to see if they could break the drought that was going on. Well, I tell you, I'm happy that the community has more patience with science now than they did then, because they only gave them 2 chances back then in Queensland. They had one experiment, fired off 10 guns, and nothing fell out of the sky. Tried again on another day, nothing fell out of the sky. They took that as evidence that they didn't work, packaged them up, sent them home. Failure of this technology. Now, what's interesting is we can look at these early experiments through the eyes of our modern science and see why they failed, why the science doesn't quite hold up that sending sonic waves would necessarily diminish hail. But it's interesting to note that you will still find hail guns in use, not only across the United States, but also in many foreign countries as well, on a very small scale. I encourage you to go ahead and look on the internet for hail gun videos, and you will have some surprising, how can I say it, surprisingly loud videos to listen to as you just hear these guns go off. There's a couple good ones online. So at about the same time, in America, there was a sewing machine salesman named Charles Hatfield. This is the trustworthy looking gentleman we see on the right, and a younger version of him on the left, who fashioned himself as a moisture accelerator. Okay, he owned some land and was just looking for ways and maybe opportunities to make some more money by seeing if he could create a technology that might bring rain to certain areas that were needing rain. Now, he had an interesting gig. Okay, so he created one of the first attempts at cloud seeding by mixing 23 chemicals together, burned them in large evaporating tanks. Now, what I'm talking about are large tanks that are like elevated 10 to 20 feet above the ground. They might be 10, 20 feet around, filled with these 23 chemicals and then burned, releasing smoke into the sky. He convinced many people that this smoke would actually seed the clouds and bring rain, attract rain to their area. So here was his spiel, is that he would agree to put one of these systems on your property to bring rain to it if needed, and he wouldn't ask for any money, not a cent until it rained. And if it rained, it was proof that indeed this cloud seeding was working. So from 1900 to 1905, he actually hired a publicist, had aggressive marketing, and had multiple contracts across the United States for small scale rain production, only taking money when it actually rained. Not a bad gig. Okay, now in 1905, the city of Los Angeles got a hold of him, and he promised them 18 inches of rain. He said he would charge them $1,000, didn't have to pay him until after the 18 inches fell. And actually, the experiment succeeded. Over 18 inches of rain fell. He took his $1,000 and continued with other opportunities. Now, an interesting case happened in 1915. Here he was hired by San Diego, where the city council actually voted 4-1 to pay him $10,000 if they could fill Morena Dam. It was a large dam, supported a lot of the community with the water that they needed. Now, Albert kind of wanted to contract a different way. He wanted to be paid $1,000 per inch of rain, but settled on $10,000. That would work as long as they could fill the dam. Well, in 1915, the winter started a bit slow. It didn't have much rain in November, not much in December. But once January came, the rain really started falling. And it fell so hard that after a couple of weeks, a couple of folks were asking him, hey, could you just stop the cloud seeding? Could you stop your machines? And of course, you just can't turn these on a dime. So he continued the experiment. Things went on. More and more rain fell. Ended up having over 30 inches of rain in 1 month, almost 2.5 feet of water. And these floods caused lots of damage to bridges, cut phone cables, maroon trains, dams overflowed, people were killed. It was really just a terrible flood event that happened. Lawsuits were threatened, of course, thinking that Albert and his machine had caused this. And well, in the end, he never got his money. Now, of course, sometimes bad publicity is good publicity, and it only made him more popular, actually. And he continued with these cloud seeding, I'll just say, experiments for a number of years. He had a couple interesting ones where he was trying to actually put out fires in Honduras with his machine. That didn't work. And tried to enhance rainfall in Alaska due to some mining areas that needed more moisture. That failed as well. Well, the Great Depression came around in 1930, and he ended up selling sewing machines once again. Now, I talk about these early historical attempts to put our modern understanding kind of in perspective. They were working from really a lack of understanding of how clouds work, a lack of understanding of how precipitation can really be enhanced or perhaps influenced by the technology we have. So I'm just going to take a couple minutes here and go through the formation of clouds and precipitation and what's really going on with the raindrops and the cloud droplets and the cloud condensation nuclei. So then you can leverage that understanding on the new technologies that we're putting in to weather modification. So what I have here is just a short video that shows, in a sense, how clouds are formed. Okay, clouds are formed from rising air. Okay, air which cools as it's rising and then condenses into water droplets. You see it happening in this video right now, as these turrets of air rising up, condensing into cloud droplets. As they're falling back down, they're dissipating. We have dry air and training in from the side, dissipating some of the clouds, but this cloud is growing bigger and bigger. This is over the San Francisco peaks. This is our view from the Belmont National Weather Service. As the base of the cloud gets darker, you can see rain starting to form. Raindrops are about 100 times bigger than the tiny cloud drops that form most of the visible cloud we see. Gets darker, more rain falls out of the cloud. And then what's kind of amusing is that this video comes to a very abrupt halt at this time. Well, let me tell you what happened. Is that I took this video about 17 years ago, within the first month that I was at the National Weather Service, first 2 months, in June of 2003. And I set up the camera on a tripod, started the time lapse, and was just enjoying the view from my office as this nice little storm popped up and pushed out a little outflow boundary. You can see a little dust in one spot. What I didn't anticipate, because I was new to the area, was the very strong winds that occur with these thunderstorms we get early in the monsoon season. And the winds actually blew over my camera, damaged my tripod, and halted the video, but at least the video was intact. So that's the first time-lapse video I've ever taken in Flagstaff, and it's one I always use to demonstrate cloud formation. So when you look at this image, the cloud droplet you see in the middle represents much of that visual cloud you were looking at in that video. Cloud droplets are typically 1 to 2 hundredths of a millimeter. So they're very, very small, okay? Now, all cloud droplets form from condensation nuclei. That is little bits of dust or little particles in the atmosphere that the water can condense on. Without it, it's extremely hard to form a cloud droplet. So you need cloud condensation nuclei and water vapor to form the cloud droplet. And that happens when air rises, cools to condensation, and condenses into the cloud droplets you see. Well, here in the mid-latitudes, it is not easy to form a raindrop. It's not that easy at all. And a lot of clouds struggle with this. And that animation I showed, or that time lapse showed that one really only formed a little bit of precipitation at the end. It's hard to get a cloud droplet of 2 hundredths of a millimeter up to 2 millimeters, make it grow 100 size in diameter, maybe 1,000 or more times in volume. But it's two basic processes that facilitate this growth. Okay, one is a cloud droplet process for warm clouds, and it's clouds that don't have any ice that allow cloud droplets to grow large. The other is in mixed clouds. When you have cold clouds, let's say clouds below a temperature of, let's say, -10 Celsius, or let's just say 0 Fahrenheit, what you see is a mix of ice crystals and cloud drops. And the growth mechanisms there are quite a bit different, but extremely efficient. So let's go through the warm cloud growth process of growing raindrops from cloud drops in warm clouds. It's called the collision coalescence process. Raindrops basically form by the collision of millions of tiny cloud droplets in the absence of ice. Now, for this to occur, it's really facilitated by having cloud droplets of different sizes. You can almost imagine why this is so, because as the larger droplets fall, or I should say the different sizes of droplets fall at different fall speeds. So it just kind of facilitates collisions in that way. The diagram on the left part of your screen kind of shows this, with a large cloud droplet falling through this field of smaller droplets, colliding into some of them, coalescing their mass into theirs, becoming a large raindrop, then the raindrop breaking apart and starting the process all over again. You can imagine that this is going on within the updraft of very warm clouds. This is a common process down in the tropical regions. It can be extremely efficient when you have enough condensation nuclei, enough droplets, and let's say a lot of salt particles, let's say oceanic particles to access, which create a big spectrum of these cloud droplets to let the coalescence process continue. But what's much more common in the mid-latitudes and where we are is what's called the Bergeron process. That's where we have this field of supercooled water droplets and ice crystals in the same area. Now, when I say supercooled water, I mean any cloud water or cloud droplets that are below freezing, but they're still in a liquid state. Because these droplets are so small, they actually don't freeze as soon as it gets to, let's say, freezing. They can stay in the liquid state at -10, at -20, even -30 degrees because of their shape actually allows them to maintain a liquid instead of becoming a solid. So we have this mix very frequently, especially at these latitudes where we are in northern Arizona and north, of a mix of ice and water in these clouds. And when we have that, the ice crystals grow very quickly at the expense of the water droplets. It actually takes on the water molecules from the vapor and forces the water droplets to shed theirs. So just in a nutshell, you could say the ice grows at the expense of the water droplets, and it happens very quickly. This is a very efficient process. And most of the rain we see here in Arizona occurs as a result of this mixed phase process that we see. So how can weather modification help these processes? Let's talk about that right now. So for warm clouds, there is an opportunity for weather modification. If we can increase the droplet spectrum, we can add more large cloud droplets with perhaps concentrated salt solutions. This is called hygroscopic seeding, because many warm clouds we see, or some of the clouds which, the warm level of the clouds have a pretty homogeneous spectrum to their cloud droplet sizes. They have a very uniform cloud droplet size, so if we can throw some different cloud droplets in there of a different size, it would enhance the coalescence process. For cold clouds, oftentimes the limiting factor is the amount of ice in those clouds. We have a lot of supercooled water, but not enough ice crystals to cause this cascading process of ice growth, which can cause precipitation. So the opportunity here for cloud seeding is simply adding more ice into the cloud. And the way that's done is adding what's called ice nuclei, or cloud condensation nuclei that ice likes to form on to form ice crystals. Or you can also just lob dry ice into a cloud, and that brings ice crystals into it almost instantaneously. These are the two primary forms of cloud seeding. We'll be talking about these later. Now, if there aren't any clouds, of course, there's nothing you can do for cloud seeding. You can't make a cloud out of nothing, okay? So that kind of brings us back to one of the questions and hypothetical situations we talked about at first. And that is, can we prevent droughts? Can we make clouds out of nothing? And really, we cannot. Okay, so how do we go about seeding a cloud? Well, for winter storms, there's three basic ways. You can use an aircraft, either to drop, let's say, silver iodide flares through the cloud in some opportune location, or you can actually put the flares on the back or on the wings of the aircraft and strategically fly the aircraft through the best parts of the storm. That is probably the most popular way to do it, because you can really target those clouds and cloud bands that you want the seeding material at exactly the right height. I was involved with several experiments in doing just this in my graduate career. Well, you can also use rockets to blast the material up and release it in those zones, or you can use ground-based generators. That's just generating this silver iodide fog and letting it loft up into the clouds. Now, for seeding rain and snow from winter storms, most of the time we want to seed it with the glaciogenic seeding materials, that is the ice nuclei. So we want to get it above the freezing level, as shown in this picture by the dotted line. We want to get it pretty high in the cloud. If we're doing the same type of seeding for summer thunderstorms, for instance, glaciogenic seeding, it's basically the same thing. We try to aim to get the seeding material high up in the cloud where it's much colder than freezing, so that the freezing of the water droplets can invigorate updrafts. Now, the way that happens is as the water droplets freeze, or as the water vapor freezes, it actually releases heat. Okay, it's a warming process. So it can invigorate the updrafts of the storm and perhaps make the storm stronger and entrain even more moisture and become even stronger. Now, an interesting side effect of the seeding of thunderstorms for rain is that you often could use, the same science would lead us to understand that it would decrease the amount of large hail in that storm as well. And here's how that would work. Large hail is formed from ice nuclei and then condenses and accretes a lot of water droplets on it, millions and millions of water droplets on these growing balls of ice that become hailstones. They're lofted in very strong updrafts in the storm. I'm talking updrafts that can be 30, 40, 50, even 100 miles an hour straight up to keep these large hailstones lofted as they're growing and growing. But what cloud seeding can do is it can provide more of these nuclei, more of these hail embryos to compete for the same amount of water droplets. Okay, so what that does, or at least what is hypothesized, is that instead of having, let's say, 1,000 very large hailstones fall out of a thunderstorm, if you seed it with the correct material, you might get, let's say, 10,000 or 100,000 much smaller hailstones. Many of those might melt on the way down. Okay, so we're seeing that the impact of treating thunderstorms and seeding thunderstorms might increase rainfall and decrease the impact of large hail. Just going to move on. Right now, states with cloud seeding programs, there's about 15 states across the United States with current cloud seeding programs. We're having kind of mixed results from some of them. I'll be talking about that in a little bit, about what kind of results we're seeing, but it's common across the Western United States. In most all cases, these experiments are to enhance the precipitation and bring more precipitation and snowpack. Up in North Dakota, it's actually a hail suppression project. Speaking of hail suppression projects, I was involved in the 1989 North Dakota Thunderstorm project. I was actually riding on the University of Wyoming King Air, shown there on the right, as a data analyst. I was kind of running the machines that were gathering all the data as we were flying through these hailstorms in North Dakota. I also rode on the Hurricane Hunter, the NOAA WP3D, in North Dakota, not through a hurricane, but through North Dakota, though I heard, at least from the pilots that have flown in thunderstorms and hurricanes, that flying through a hurricane is actually easier because the flow is a lot more laminar and not as up and down as it is in high plains thunderstorms. Well, I was also involved in the Arizona program in 1995 for my postdoc. And here I was actually looking at, is cloud seeding viable in northern Arizona? And specifically, directly for our neighborhood here in Flagstaff, that is, can we seed clouds and increase the precipitation and snowfall over the western Mogollon Rim? We really have a unique situation here in northern Arizona, and especially from Mingus Mountain on the west side of the Verde Valley to the Mogollon Rim, to set up kind of a cloud seeding program here with the way that the storms form this upslope precipitation field on the east side, the Mogollon Rim. there's a very natural way that we could seed those clouds, and that would be from the top of Mingus Mountain. We could have like a static seeding generator on top of Mingus Mountain, releasing the seeding materials. It would get swept down on a static wave and then back up into the upslope region of the precipitation that might fall on the Western Magellan Rim. So we actually did a number of experiments. We saw that indeed we could entrain the seeding material up into the clouds. We saw that indeed we could also seed from an aircraft. We traced some of that. But because of the limitations of the measurements, we really didn't have any direct observations of any benefits, of any impacts from the cloud seeding and the testing we were doing, at least in this experiment. We could talk a little bit about hurricane modification. There are some fun experiments going on in the 1940s and the 1960s and 70s. And I'm going to talk about one here. This is Project Cirrus with Hurricane King in 1947, where what they wanted to do was seed a hurricane and try to basically collapse the eye wall through increasing the rainfall so much, okay, in the outer bands that it kind of collapsed the eye wall and weakened it. So they tracked this tropical depression to the north as it crossed Cuba, as it came across to the east past Florida, and found an ideal candidate in this hurricane. It was headed out to sea. It wasn't going to harm anybody, so they could seed it and see what happened. So late on October 13th, they did just that. They flew their aircraft out, hit it with a whole bunch of seeding agents, stuck around for a couple hours, and saw that indeed it looked like more rain was forming, the clouds were getting stronger, and it might actually collapse the eye wall. So they hustled back to land the plane, waited till October 14th, flew the plane back out there, and tried to find the hurricane. Well, they had some trouble finding the hurricane. It was really interesting. They flew back to where they thought the hurricane would be. It wasn't there anymore. They kind of extrapolated where it should be farther northeast. It wasn't there. They turned to the west and saw that the hurricane had actually made a left-hand turn and started heading toward the Georgia coast. Not only that, but it was intensifying and strengthening at that point. It landed late on October 15th as a pretty strong hurricane, which caused 1 death and over $2 million in damage. Well, you can imagine the public outrage from this, from a known seeding experiment of a storm that was headed out to sea and all of a sudden turned back toward the land right after they seeded it. Now, science since then has showed it that this was just the way that this hurricane was going to track, given the large-scale weather patterns. The seeding had nothing to do with it. But at the time, there was public outrage, lawsuits that were threatened, and it caused this project to be canceled almost immediately. Okay, and since then, there really hasn't been much in the way of hurricane modification experiments. But there's, hypotheses for just what else we could do to perhaps intervene and in hurricane formation, or even modify a hurricane after it's formed. This came from Scientific American in 2004, Russ Hoffman's work, to where he hypothesized, we could put maybe a huge biodegradable oil slick in the ocean in front of a hurricane, and maybe rob that hurricane of the evaporation of the water moisture that it might need. We could heat up the water vapor around the hurricane from an orbiting power station, perhaps robbing it of the local humidity that it needs. Or, like was hypothesized could be done with Hurricane Iniki, which struck Hawaii, that maybe if you just seeded one side of the hurricane, it might steer it in different directions. Very interesting hypotheses, none of which have been proven. We're still trying to work out the details, but it's fascinating to think about some of this. So let's get back to our original question. Can we control the weather? In summary, no, at least not yet. But what can we do? We can influence or enhance some cloud processes. And right now, I'm just going to take a couple minutes to end this talk with the current state of the science and what we know. So as far as weather modification to dissipate fog, you bet. That's something we can do. It's been implemented for a number of years, economically viable where fog is frequent. Yes, we can modify fog. We have good results for warm fogs, which don't have any supercooled water in them, simply by heating the ground through massive heat generators. For supercooled fogs, which are just masses of supercooled water droplets, we only have to toss in a little bit of ice, and it converts so much those water droplets into ice crystals, which simply gently fall out and clear the sky. You can see many examples of this online. It's fascinating, and it's done frequently. How about cloud seeding to increase precipitation? Now here, it is very difficult to quantify results. And you can kind of imagine why. There's direct observation, which is lacking. That means if you throw seeding agent into a cloud, how do you track that agent to see if it actually made a difference in the clouds? Also, there are statistical issues. That is, if you seed, let's say, 100 clouds, well, how do you know that those clouds weren't going to grow more anyway or cause precipitation anyway? It's hard to have a null case versus a positive case when there's so much variability with each and they cross each other's realms. So it's still economically very uncertain. But what we have seen in a number of experiments across the world is that the best results for cloud seeding are for winter storms in the mountains, especially when the winter storms are coming up a significant slope where we have orographic precipitation. Though success is kind of limited for enhancing summer storms. We really haven't seen much success in enhancing rainfall from summer storms. I mean, there's some which seem to be very successful, other experiments not. But right now we're looking at, through cloud seeding, under specific conditions, we might see a 2% to a 15% increase in precipitation. Now, this isn't for all storms. This isn't for all areas, but under specific conditions, maybe 2% to 15% increase of precipitation. For cloud seeding to reduce hail damage, again, very, very difficult to quantify the results because you don't know which storms were going to cause large hail and which ones weren't before you started seeding. The results are mixed. If you kind of do a rigorous analysis, you'll see that out of all the experiments in Switzerland, they might actually have an increase in hail from their hail suppression efforts. Argentina, kind of a mixed bag. I've had a number of years of experiments there. In the Soviet Union, they claim to have massive success with this. Results in Alberta, Canada, and North Dakota also show possible economic benefits and perhaps some very positive results. Again, it's hard to have rigorous verification without direct observation. You need that direct observation if it's available. Okay, and we have a number of different types of weather modification which are still theoretical, not viable, or not economically reasonable. That would be hurricane modification, drought prevention, lightning reduction, tornado prevention. There have been some theoretical experiments done, but nothing has shown to be viable at this time. But let me tell you something really exciting. Just want to take the last 2 minutes of my presentation to tell you about some new research that just came out. First part came out in 2018, and the last part just came out. I was just made aware of it today, and it appears in an article. It's going to come out on October 2nd, and that is we now have our first direct observational evidence that cloud seeding can create precipitation. Okay, we actually have direct evidence, and I'm going to show you exactly what that looks like. Okay. This is it. Now, I know this is kind of a meaningless, colorful picture right now, but let me explain what you're looking at. You're looking at a vertical cross-section of the atmosphere. The black area on the bottom represents the topography under this area of cloud and precipitation. Where the storms have larger crystals or heavier rainfall, it's in the yellow or red. And this white line shows the white dotted line through the middle, shows where the Wyoming King Air was flying, basically to take these observations. And what this shows is a radar image showing an area of enhancement in that cloud in exactly the location that they seeded. What they were able to do is follow this for over an hour to see what happened to it. Okay, 10 minutes later, the seeded area was, we had crystals growing in it. It was becoming brighter on the radar. It was becoming more intense. It was growing quite rapidly. A half hour later, now it's moving with the wind from the left to the right. We see that the original seeded area is still there, and another one popped up. This was another area that was seeded, is intensifying and actually now creating snow all the way to the surface. You go on in time, this is a half hour later. These areas are now showing moderate snowfall reaching the surface in each one of these seeded lines. Now, what's exciting about this is the Wyoming King Air aircraft was actually flying through this exact same area, sampling the ice crystals, sampling the water droplets, and actually taking direct observations of what was happening at this time. It's exciting research. It's called the Snowy Project. Jeff French from the University of Wyoming wrote this groundbreaking article in 2018. Okay, and this is just in, stop the presses, to be published on October 2nd here. The Snowy Project has now quantified the amount of precipitation increase during these experiments in Idaho. Okay, they've actually quantified the amount of snow that fell. They took all the information, took the aircraft data, looking at the amount of snow crystals, the amount of water droplets, looked at the radar reflectivity through the entire area. And here's what they found. They found that the precipitation increased where they did their experiments between 0.05 and an inch and 1/3 of an inch. Okay, that correlates to, let's say, about 1/2 inch to 3 inches of snow in this area. From one experiment alone, they estimated they created an additional 275 acre-feet of water from just 24 minutes of aerial cloud seeding. That's just from one aircraft. Understand this is about 900 million, or I'm sorry, this is about 90 million gallons of water, or enough to supply 400 homes in California for an entire year. Now, this is fascinating stuff. I wish I could talk more. These are exciting times to be involved in weather modification. So I'm just going to cut it off right there and take a few minutes for questions at this time. Thank you so much for being with me this evening.
Wow, thanks, Brian. Fascinating stuff. I love your excitement about it. Yeah, we have about 10 minutes here to answer some questions, and there are a lot of questions coming in. And the first, so we'll go straight to the questions. A couple of questions came in that are related, and so I'm going to ask them sort of both together, okay? Well, one of these questions is from Peter in Flagstaff, and he says, the science is quite interesting, but with everything so connected, how do we know that weather modification going on around the world hasn't played a role in the climate changes and issues we're seeing today? And another related question is from Sarah in Flagstaff. And she says there are multiple situations throughout history of messing with nature for human need, such as predator removal to increase deer elk populations, which turned out to be a bad thing for the ecosystem. So what guarantees do we have that this isn't going to be bad for the ecosystem? In other words, just because we can do it doesn't mean we should do it. So I think those two questions are sort of related, and you'll probably want to take some time on those.
Boy, excellent questions. You know, there's been a lot of research done in exactly this topic. That is, do you pay Peter and Rob Paul when you're doing, let's say, cloud seeding? Are you precipitating out rainfall that's going to fall in one location that should have fell in another? That's a common argument, or at least an issue that a lot of people are concerned about. But science has shown that that's really not the case. It's not the big case because we're treating, actually, when you think about a huge storm system and all the moisture which is feeding into it, we're only impacting a very small part of that system, okay? We're only doing it for a very short amount of time. We're also trying to make one local system more efficient. Now, I said that it's the most efficient, and one of the conditions that it's most optimal to have cloud seeding is in areas of terrain, let's say mountains. As that air mass moves off the mountain, it often dries out on the other side. That's why, let's say, Donny Park is so dry. The mountain itself squeezes out all the moisture, and on the opposite side, it's quite dry. On a much larger scale, let's say we have Death Valley, which is very dry. Just because we're cloud seeding on one side of a mountain doesn't mean we're allowing for less precipitation on the other. Or even farther downstream. There have been numerous experiments that have shown that within the volume of the atmosphere, which the Earth has, these experiments and the opportunities for cloud modification impacts a small area and can provide the benefit to that area. Another question which is brought up is, hey, if you're throwing all this silver iodide up into the atmosphere, is that harmful? Is that harmful? Again, this has been done and shown in numerous demonstrations that the amount of silver iodide with at least, the experiments that are going on here in North America is barely above like the ground level, meaning it's not an amount which is going to harm you, but it is an amount we can actually detect, so it is there. And oftentimes it's actually seen as a verification that yes, we were able to get the seeding agent into one specific area. Excellent questions, very viable concerns, and it's an area that I'd like to see more research on myself.
Okay, cool. Here's a question from Julie in Flagstaff. With our current non-soon in Flagstaff, should we start cloud seeding here? And Kevin in Flagstaff also asked the same question and wonders if we should be engaged.
Great question. Well, if we don't have clouds, can't do any cloud seeding. It won't help at all. And unfortunately, this monsoon we've had that has, wouldn't even allow that possibility to happen. One of the things I said up front is right now we just don't have the technology, or at least the ability to impact droughts and the ability to alleviate droughts. We can make, like I said, minor perturbations and minor impacts on some clouds that might have more uniform CCN or uniform cloud droplets or not enough ice crystals. Those are the ones we might have a little impact on, and that's even at that, it's only 5 to 15%. Though these, results that came out of Idaho, out of the Snowy project, actually are very exciting for the scientific community. It's great to see the direct observations, because now we can understand a little better what impacts we're having when we do the cloud seeding.
All right. Let's see. Let's go to Kim in Flagstaff. Where do you see the future of weather modification going?
Boy, great question. I see a lot more modeling done so we can understand this huge system that we're trying to impact. I don't think we should be throwing let's say, materials willy-nilly at clouds without a complete understanding of what's going on. So the results that just came out of the Snowy project will be invaluable in fine-tuning the weather models we have to see just what the impacts can be if it's scaled up. Okay, it will kind of give us some ground truth to the scaling mechanisms, maybe ramping this up and see what happens. Maybe we will learn more about just the longevity of these weather modification impacts. Let's see, where else might this go? As water becomes a resource, which is more and more scarce. I mean, and with climate change, I think just the shortage of water is going to continue to be a major issue, and we're going to continue to do all we can to bring as much water out of the atmosphere as we can. So I suspect that we're going to continue to see more funding in this direction to try to alleviate some of the droughts that we're seeing in some way.
Okay, cool. Yeah, we have about 5 minutes to go, so we can take a couple more. And there are a number of questions rolling in, so I'll try to get to them all. We may not get to them all, but right now we have a question from Allison in Flagstaff, who asked a really interesting question. Could this technology, or should this technology be used in firefighting? Thinking about California right now.
Boy, you know, that's a great question. I would say yes and no. When you have active fires on the ground, you have soils that are very sensitive to rainfall, okay? And while a fire that might be put out by a storm, that storm might also cause catastrophic debris flows and floods from those freshly burnt soils. So it's a very difficult question to actually address. Would the threat of flash floods outweigh the benefits of putting out the fire? Again, you need clouds in order to do cloud seeding. Without clouds, there's nothing we can do. And tough question, but it has both positives and negatives that I could see might also make it impossible to address that.
Okay. There's another question here from Connie in Flagstaff. How do smudge pots in orange groves reduce the threat of frost?
Oh, interesting. Great question. Great question. I'm not too familiar with the technology, I'll be honest. If these smudge pots, well, I guess I don't know, because I don't know what a smudge pot is. I guess in my mind, I have some ideas of what it is, but I don't know. I know that in some areas, they have very large fans that actually circulate the air and inhibit the inversion from forming. You know, cold air sinks to the closest area of the ground. And if you have sensitive crops low to the ground like orange groves, you can actually circulate the wind and bring down some of the warmer air from above. Smudge pots, I'm not sure about the technology. I wish I could help you out there.
Okay, I think we have time for another one. This is from Virginia in Flagstaff. Are there any current weather modification projects going on in Arizona?
I just looked that up because if you notice, they were highlighted on that map that I showed back in 2018 is when that map was created, showing ongoing cloud seeding projects. I couldn't find any at this time. What there is there's funded research on cloud seeding at the time, but I'm not aware of any cloud seeding projects or any weather modification projects going on over Arizona at this time.
Okay, well, that was fantastic. A lot of interesting information there, lots of good questions. Thank you, Brian. As I'm pulling up the very last question, I just want to say thanks again. Thanks to everybody for watching. Remember, you can go online to our webpage and take the feedback survey. Let us know what you thought about the presentation. Okay. Can't find the most recent question, but we're just about out of time anyway. So, well, I guess we'll just stop it there. And
all right.
Say thank you.
All right. Well, thank you, Greg, very much. Thank you, everybody, for your time and your great questions. And stay in touch. Science is fascinating.
Thanks.